Hello, welcome to Security, Cryptography, whatever. I'm Deirdre.
I'm David.
I'm also David.
No, you're not. And we have a special guest today, Eric Rescorla. Hi, Eric.
Hi.
Hi, welcome. For those who don't know, Eric Rescorla has been intimately a part of designing a more secure internet. And we are very happy to get to have a big, deep dive on various internet security things, including SSL and TLS. How did you get started on SSL stuff, which we don't want to use anymore? And we're a big part of TLS 1.3, which is like the most modern in network security, internet security protocol that we do like and do use.
So if we scroll back to like 1993.
Oh, God.
I worked for this startup called Enterprise Integration Technologies. It was in Palo Alto that sort of did a lot of like DARPA contracting and stuff. And the people there were very enamored of the web. And when the web first came out, everybody sort of knew that like the web needed some kind of security. And there was like a bunch of flailing around in that area. And as part of like one of our contracts, we actually started trying to design some security for the web. And we designed this thing called Secure HTTP, which did not take off. And at the same time, Mark Andreessen actually worked for EIT for a very short period of time and was sort of involved with that project. And then when Mark went to found Netscape, they decided they wanted something, and they decided that Secure HTTP was bad and they should build something better. And they built SSL. And in retrospect, like they were right and we were wrong. We had sort of this design that was very tightly integrated with HTTP and was like much more like message encryption and message signatures. And they were like, well, we're just gonna do something simple, which is SSL. Okay. And so, if you've read that famous, Dick Gabriel, worse is better design, this is a classic worse is better design.
Can I stop you and ask a question just out of morbid curiosity?
Yeah.
How bad was the cryptography in Secure HTTP?
It wasn't terrible. It was like, S-MIME basically, the binding to, like basically a way to think about it is like your S-MIME encrypting HTTP messages, right? Or signing them. The weakest part was probably like the binding to the identity was not like well understood.
But like SSL got like basic secure transport things wrong, like the weird CVC mode type stuff and all that. Like,
I don't think. I mean, we mostly just like ripped off like S-MIME or I think it was like S-MIME or MOS, which you may recall was like another attempt to do secure object encryption for email. So since HTTP was modeled on email on 822, right? We were just like, well, we'll rip off all the email stuff. So I think that part like. I mean, I don't want to promise any of it was very good, but I think that part probably was a little closer. The part that I think was less good was, aside from the clunky parts, was like we didn't really have any notion of origin. Whereas I think, it was much more like, hey, when we give you a link, we're going to give you also the key material to use that link, which I think in retrospect was probably a mistake.
Mm-hmm. And so you got usurped by SSL and Netscape.
So I think, EIT spun off this company to do, so there for a while, there was kind of this like optic of like, there's like a protocol war between Secure HTTP and SSL. But like when one company is this tiny startup and one company has like basically every web browser in the universe, I think who's going to win that protocol war. And so EIT spun off this startup called Teresa to basically do SSL, TLS, SSL at the time, and also Secure HTTP toolkits. And I think that's, the Secure HTTP part was like intended to be like, we didn't just lose. And I went to that startup and then for a while I was doing like SSL toolkits. And, at some point just like got to be doing a lot of SSL and TLS largely by default.
I think I've completely underestimated how long you've been at this because I just didn't realize. And you've literally been there since the beginning and blah, blah, blah.
Yeah, we had like a V2. I think we had a V2 stack. We definitely had a V3 stack. I remember when V2 was introduced. And as you say, V1 had like actually a number of quite serious, V1 never really saw the light of day. It had a number of fairly serious errors in it. V2 was better.
That's another thing I'm super curious about that I've never gotten a chance to dig into is the SSL world for me starts with V2. And like, I'm also super curious about how bad V1 was.
So V1 and V2 aren't that dissimilar. I mean, I don't think I ever saw V1. I think it was like only presented at some, circulated in kind of like private emails and then presented, I think, a couple times. And I like, if I recall correctly, it was like RC4 with no integrity check or something. I mean, I think you have to. I mean, I think you have to understand like how little anybody knew about designing secure protocols back in 1993, 94.
Fair.
These things were designed like about the same time applied cryptography came out, to give you a sense of the timeline.
The big red book.
The big blue book.
Oh, the blue book? Wait, which one? Okay.
Applied Cryptography 1 was blue.
Oh my God. All right. I feel I was like a tiny baby at this time. So, I mean, literally, I was a 6-year-old.
It wasn't as big. It was like, I don't know, 2/3 as big.
There just wasn't enough cryptography. Now we have too much crypto, and now there just wasn't enough crypto at the time.
There's a lot of wisecracks I could make right here that I'm not making. So.
I want you to make wisecracks. It's our podcast. We can do whatever we want.
I got to work in this industry.
That's fair. Okay. So we deployed V2, V3, and then we turned into TLS1 and TLS 1.0, 1.1, 1.2, and then you spent years and years and years basically leading the 1.3 effort. Can you tell us? Tell
I mean, these are some of like the worst
marathon.
names. This is the worst naming in the history of humanity.
Right, because 1.3 is incredibly significant, and it would be TLS 2.0, but for the like ossification of protocol numbers on the internet, right?
Well, also marketing. You know, I mean, so like I think that the naming, right? So no one wanted to like be like, for the early versions with SSL v2 and v3, no one wanted to be like, we totally rebooted everything. And then TLS got renamed because the IETF felt like, you know, if we're going to take this on, the one concession we're going to make to not just taking exactly what Netscape did. Well, I guess a couple concessions, and like one of them was like, oh, we're going to like change like the hash functions a little bit.
Yeah.
And another one was we're going to rename it. And then like when we did 1.3, I think I was worried that people would be really afraid if we decided to call it TLS2. It'd be safer to like suggest it was a minor increment. And I thought it was going to be a more minor increment than it was, honestly. I mean, so, the history here, right, is that there have been sort of a series. I think we thought it was done. Like that 1.2 was done, you know? There was kind of like an end of history feel when people were like talking about taking it to draft standard and full standard. Because, you know, the IETF is this goofy, multi-tier standards thing.
That no one but IETFers
like
really understands
standard,
the difference.
Right? Like practically everything important is like a proposed standard.
I feel like I've paid a lot of attention to like the TLS working group and all that and not realized this. So at the time of TLS 1.2, TLS was not a full standard.
TLS has never been a full standard.
It's not a draft. It's somewhere between draft and full.
It's a proposed standard, right? So so like the RFCs get issued at proposed standard, basically. And then there's this ornate process that take you to full standard that like people just don't care about because like for the reasons you're talking about, nobody can tell. So they used to be 3. There was like proposed, draft, and full. And then it got so embarrassing they got rid of draft and then just mass promoted a bunch of things to full. TLS 1.3 is also not full. It's all proposed. In fact, Sean, the chairs have been suggesting we take it to full, and I just told them I wouldn't do any work on taking it to full. And I was happy if they did it, but I wouldn't do any work on it.
Yep, this is a thing that like no one in the rest of the world even cares about. It's literally, is it an RFC? And then they can point at it, and it's mostly static because of the way that RFC documents work. And then everyone inside the IETF is like, it's not a standard yet. It's not standard. And like everyone else in the world calls a thing with an RFC number a standard. This is all just talking past each other with different words. But anyway.
I mean, long story short, TLS is maybe the way that we're going to encrypt the web.
Yeah, that seems likely.
Yeah.
So I think, we sort of thought it was kind of like, kind of done, right? And then like a series of things happened. You know, I guess I would say probably the 3 biggest things are, 1, a lot more pressure on like the privacy aspects of the system, where there's just a sense that way too much of the handshake was in the clear. The second was, I think, quick crypto and the feeling that the performance was not like what people wanted, and that like burning a whole round trip to get the first byte was bad. And so I think those are I think the first 2 kind of things that made people think maybe they do something. And then sometime around this time was triple handshake, and that was the first like real significant attack on 1.2 in like a super long time. And suddenly people were like, maybe actually we don't understand the system as well as we think we do. And it was the first, I think, real formal and analytic result where someone had tried to model TLS and it come up short, right?
Resulted in the triple handshake attack.
Yeah. So what happened was those guys were writing, the InRio Microsoft team was writing like a verified stack in which I cannot recall the name of it at this moment. And they like basically as I understand it, you should have to Karthik, but as I understand, a number of the defects that they found eventually were the result of like basically proof gap in trying to like build like, no, the proof doesn't work. Why doesn't it work? Oh, well, now we have a problem. So I think, Triple Handshake came out and was like, okay, now we actually need to do something, like we need to clean up things. And I sort of thought this was going to be a fairly quick win. I thought we sort of understood. There've been a lot of prior art, especially on the zero round trip stuff. So there was, this goes back really far. So I mean, you probably know about Snap Start, which is like Langley's thing. But like, actually there's a paper called Fast Track by Benet and Shockham, and eventually it turned into a journal paper that I was on that like had the same kind of thing of memorizing the server's parameters. So like Fast Track was like memorize the server certificate and use RSA, a single round trip RSA to initiate the handshake. So there's been a bunch of like stuff going back very far on how to shorten the handshake. And so I just sort of thought at the time naively, we'll just rip these things off and cram them into TLS and extensions and call it a day. And that obviously did not work out. It took about 5 years to get from start to finish, which is like not unusual.
Honestly, I thought it was longer, and hearing 5 years for the not monstrosity, but just like it's a big significant chunk of work that is 1.3 doesn't sound that long to me. So
I mean, Quick was about 5 years too, from like start of IETF to finish of IETF, and it probably had like 5 years of Google, machinery in it earlier. So I think, it sort of started small and kind of snowballed. And I would say probably the two biggest things that I think snowballed it were, one, getting the academics interested and starting with Karthik and the Rear team, but then also, Dennis Davila and Cass Kremers and his group. Suddenly we have like a real bench of people you could go to. Hugo Krawczyk, I can't wait to forget Hugo Krawczyk. Suddenly we had a real bench of people you could go to, and you could say like, well, what if we did X, Y, and Z? Would that be okay? And then eventually I got to the point where they'd say, well, we actually have verified this and like we have some level of confidence it's right. And so I think that was the first thing. And the second thing was, I think this is largely due to Nick Sullivan, was getting a real community of early implementations. And so Nick sort of, the IETF's been doing this thing called a hackathon, basically where there's like a couple days before the meeting. And so Nick was like, we need to do basically an interop for 1.3 and really drove that. And so suddenly we had people sitting there for 2 days actually trying to get interoperability. And I think those two things suddenly basically turned something, which I think was a bit of a boutique effort into something where it was like a giant cast of people all working on it and trying to wrangle it. I think we planned, I tried to sort of keep this going with we had to do a bunch of workshops very early on. And there was like a lot of uncertainty at the beginning at what this thing was going to look like in general. And some things got kicked off that we actually wanted to keep. I would say ECH being number one, which of course comes back later.
It's back.
Yeah, it's
encrypted client hello, for those not familiar.
Right, yeah. So I think, maybe to touch on that for a moment, TLS 1.2, none of the handshake was encrypted meaningfully.
Yeah.
And this includes the two most important pieces of information in terms of privacy, the server certificate and a client certificate. And 1.3 drives the encryption much earlier on, so that both those things are encrypted. But it turns out that encrypting the server certificate only gets you part of the way there.
Yep.
Because literally the first message the client sends contains the domain name of the server you're trying to connect to. So until you get rid of that, you don't have much in terms of privacy for the server. The client is much improved.
Yep.
And so everyone knew this from the very beginning, and there was sort of a bunch of attempts to try to fix it. And no one could quite figure out how to do it without like burning a round trip. And since part of the point of the exercise was to make it faster, no one was going to burn a round trip. And so we had to throw it off the island, and then eventually it kind of came back once we figured out how to do it without burning a round trip.
And how do you do it without burning a round trip?
I mean, you prime in the DNS, which everyone kind of knew. So I think, going back, I kind of sort of say like, how didn't we know this? And I think that the real thing that happened was we knew about DNS priming, of course, but no one thought it was plausible. And so the history of this is, we'd given up, but I was going around telling people like, don't expect encrypted client hello anytime soon. Like we sort of thought about it for a while, and there've been a bunch of there was like an RFC published like an analysis of the space that kind of like has sort of a negative conclusion of like how it's getting really difficult. And I'm going around telling people, don't expect encrypted client hello anytime soon. And then one day, Matthew Prince emails me and is like,
the CEO.
Yeah, why don't we just give you Firefox a public key for Cloudflare? And every time you catch a Cloudflare domain, you can encrypt, the server name indication. And I'm like, that's a pretty good idea. But an even better idea is once you realize you only really have to solve the CDN problem,
Yeah.
then the CDNs control the DNS by and large. And so then the problems start to look more tractable. So I think like really, no one really thought there was going to be enough DNS imprinting, priming from regular domains. But once you say, oh, we're only really solving Cloudflare and, and Fastly and whatever, something that's a more tractable problem. And so we pivoted from nothing to like, oh, we're not working on Deca to do this, to actually, well, no, we're going to try to drive this forward quite quickly after that.
And like having, those are major players. They're serving or fronting a large part of the internet. Your Cloudflares, your Amazons, your Akamais or whatever. And like they do.
Your flies.io.
Exactly. Yeah. Flies.io. No, I love that. I love
your
that.
flies.io. So like something is better than nothing, even if it's like literally you have to have a buy-in from a DNS controlled provider, blah, blah, blah. On the other side of that, how do you feel? Less so much how do you think, but how do you feel about security lives in the gaps between abstractions, right? And so we've got TLS, a cryptographic protocol that we're negotiating at this layer of, the TCP IP stack and all this crap of the application layer. And then we've got DNS up over here and they're kind of integrating and how do you feel about making this of TLS rely on these parts of their sort of just reaching outside the abstraction level that you're designing stuff at? Because I know I'm just sort of like, it's not the best, but it's also the world that we live in.
Yeah, I mean, I don't love it. I mean, like if you read the document, there's this like long rationale of why like it's okay for this to be in the DNS, even the DNS is like entirely untrustworthy. I mean, I think, it's just clear that like we go and we try to design these things that are perfect. And then you reach contact with the real world and you suddenly have to make all these compromises. And one of those compromises is the fact that like a huge fraction of the internet, it just cannot be changed in any meaningful way. And so you can only operate in like the zone of what can be changed. So it'd be better if we had some other way to do this, but we don't.
I mean, we'll touch on this like later, but like your take is like you go into it like an idealized design and then it hits the real world and everything goes haywire, right? But like the other way to look at it is you go into it with a coherent design, right? Like with an actual service model with like, some kind of like formal rigor behind it. And then it hits the real world and it is no longer coherent, which is a more significant, I think, thing to say, and just in a computer science sense, than like, yeah, it's all fucked up because like the world is fucked up, right? But it's more than that. It's like, it's in some of these cases, the designs we get are just incoherent.
Yeah, that's right. I think the question is can you maintain some coherency, or did you just like, as you say, we'll talk about this later, but I think like often you'll see designs that have like if you sort of took them all together, seemed really sound. And then when you realize all the compromises that got made, you actually asked, like, was the thing actually work the way it was supposed to work anymore by the time you made those changes? Yeah. And that's something that you're really, really attuned to. I think maybe to circle back for a second, TLS 1.3 was sort of like the second big iteration of the model we're now seeing for protocol deployment. Which is you get together like a club of people who are like really motivated and control big parts of the internet, and they just do it. And so that's how you go from 0 to 50% in a couple of years, and how you get, massive quick deployment and massive TLS 1.3 deployment and massive HTTP2 deployment. And HTTP2 was like the first generation of that. And I think like Mark Nottingham and Martin Thompson and, Ian Fetty and like all the people who did that deserve a lot of credit for kind of like seeing how to like get this. And then I think 1.3, brought in like a bunch of the CDNs as well as kind of the Googles and Facebooks of the world. Yeah. And you just see Quick following the same pattern. And like WebRTC is a little like that, but not quite as much. But this is like how things happen now, because you have these systems where there are 4 major browsers and those people can roll out changes inside of 6 weeks. And they're, and when you add up the big CDNs and Google and Facebook, how you basically control just a giant fraction of the server traffic on the network now. On Amazon as well, but Amazon is a slower mover typically.
Okay, interesting. I keep forgetting that TLS 1.3 was the first to be formally modeled. Like, well, you mentioned that these vulnerabilities were found in 1.2, with the first attempt to be formally modeled was only like late in TLS 1.2. And we only kicked off 1.3.
Like 8 years after, right? I mean, because 1.2 is like released in like 2008, right?
Yeah, that sounds right.
And by the way, I just go back to this deployment point, had almost no deployment. I joined Mozilla in, I think 2012, 2013. Like it wasn't even in Firefox and it wasn't in Chrome. And like one of the first things I worked on was trying to like drag it into like Firefox and Chrome, find in Firefox.
Seriously?
Because we went to GCM and GCM came in with 1.2. You were saying formally verified though.
Yeah. I'm mostly just like flabbergasted because there's been so much analysis, especially like for 1.3, it was like this constant churn of like updates every time that there was a new version. And it's kind of flabbergasting to me that like we basically only barely did anything with 1.2 before we kind of turned into 1.3.
Yeah, I mean, I think my sense of how that happened is that I think two things. One, just no one's interested in doing in 1.2. I mean, like 1.2 and 1.1 are very similar. 1.2 is basically 1.1 plus like new hash functions. And so I don't think anybody felt like, people felt like they understood the properties of that. Maybe they did, maybe they didn't, but like they thought they did. And 1.3 was, obviously it's big changes, and people I think felt like it was good. Like there was fertile ground, and B, was an opportunity to get in the ground floor and do something that people cared about and was meaningful.
Yeah.
And I think also there's a confluence of like the tooling was better. But by the time we did it, suddenly there really was tooling you could use for this.
Yeah, that's a good point.
I mean, you would I would seriously message Karthik and like, and be like, can we try this? And Karthik would come back to you like a day or two and say like, this seems okay, or I would not do that. And I put together some little Proverif model, and that just wasn't possible in 08.
Yeah, that's a really good point.
So I think we're nearing a tipping point, where everything is going to be that way. And, to flog something you've done, I think this thing about where TLS is now going to have a panel of, of formal verification where everything can kind of go through that, I think is incredibly important. I feel terrified every time I touch one of these things. And so I want to have a safety net. And so I think that's incredibly important.
Oh yeah, we hopefully will get this episode out before I send out the summarize from the first round of that. We've done one iteration, which is great because I was worried nothing would happen. And one thing that you said earlier was like we've had our easy crypts, and we've had a couple of other computational tools that like are just too much for a protocol at the scale of TLS. And so you move over into the symbolic provers like Tamarin or Perva. And I know they kind of showed up somewhere in 2008, 2013 or something like that. And having people like Karthik and Cass and Douglas Ahula be able to drive them really helps, because if, I know from my own experience that like I can sort of make sense of these models, but I need to ask them to be like, I think I did something useful. What do you think? One of the things you said earlier that kind of stuck out to me is like, oh, we thought TLS 1.2 was the end of history. We thought we were done. Do you think we're done with 1.3?
I think we're clearly not done. The obvious thing is the post-quantum transition. Which, maybe we're going to get lucky. I don't know. I don't know who I speak for, but like, I think I speak for a lot of people, and just hoping the algorithms are good enough that we can kind of just like, cross out the EC and write in modular lattice and call it a day.
I wish. But
like, that doesn't seem to be the case necessarily, at least for the authentication pieces. And of course, God help us if it turns out those things aren't secure. Then we're really in trouble. I would like us to stop messing with things so much on this layer. The question is, what do we have to do with this layer versus other layers? Like, obviously it has to be good. Mm-hmm. And if there's important things to do, we obviously have to do them. If it's broken, we obviously have to fix it. But the question I would ask is, when I look at the security problems of the internet, are these the biggest security problems of the internet anymore for us to apply our effort towards? Yeah. And in particular, part of why I spent so much time at ECH is I felt like part of the problem that we had these privacy problems to fix. And I think, we've made relatively scant progress on those privacy problems. And the ones we have made progress on, we've done by managing to kind of reshape them into ComSec problems. And sometimes that's worked and sometimes it hasn't worked. And I think, if you like ECH maybe will work, but like, are we going to solve the problem IP addresses by like reshaping everything in a mask? I don't know. No. That seems like a pretty tough sell to people, that everything has to get proxied through two proxies in order to like protect your IP address.
Yeah. Was that, what do they call it for Apple? Like private relay? Yeah. And it's like basically their own spin on a onion routing and sort of deal.
Yeah, I mean, it's really nice work. I mean, it's good work, but it's just like, can we really afford to have an internet where everything is proxied like that? And if not, like, what do we have?
Yeah. Speaking of improvements or where we can focus our work, I don't remember what year it started, but sort of trying to assure that the web PKI, that the certificate authorities that almost all of TLS connections rely on in one way or another to authenticate the origin that you're communicating with, the server that you're communicating with, via a chain of trust to some certificate authority, we basically started working on certificate transparency, which is a way for independent auditors can see whether a certificate they're looking at was legitimately issued by a legitimate CA. At the very least, there is a promise that it will show up in a certificate transparency log at some point in the future. Can you tell us a little bit about certificate transparency?
It seems simple, right? Like you just, all you do is you have, all of the CAs sign all the certificates as they issue and then publish them. And then the browser just checks the signatures on the certificate. And it seems like a very simple thing to do. So we solved this problem, right?
It's a Merkle tree. What could it cost? $10?
Yeah, exactly.
This is going to be a quick part of this episode.
Yeah. I mean, so it's probably worth starting with the logic of this design before we talk about the implementation. And the logic of this design is what we're concerned about is surreptitious misissuance. We're concerned about misissuance that is undiscovered. And the assumption is that somehow, if things are discovered, we will fix them. Let's just bracket that and assume that part works, because that's a whole different piece of pain. And so the underlying design, the assumption is that we will find a way, as Thomas says, which is every certificate in the world we publish. And an example, and I usually use the analogy of there's going to be a giant laser that every CA has. And when they write a certificate, they're going to inscribe the certificate on the face of the moon. And then when you get a certificate, you're going to pull your telescope and look and see something on the face of the moon. If it's not there, you don't accept it. So that's the first half. And that's the part that ensures that it's published. And then the second part is that everyone who has a certificate, has an origin, verifies that there are no certificates for their origin that are not the ones they expected.
Right.
So if you're example.com, you go look and you're like, why is there a certificate for example.com with a key I don't recognize? And if there isn't, then again, you complain and hopefully something happens. What happens, again, a little confusing. So that's the logic of the situation. And then that's a sound logic. We see that logic being exported to other things, for especially for end-to-end messaging. I think the implementation, got overseas a little bit, in that there are sort of two ways to build this design. One is what you kind of call a centrally trusted design, and one of which you call a zero trust design. And so in the centrally trusted design, you would basically say, as Tom has indicated, you would publish your certificate to somewhere, and then the place you published it would basically be responsible for guaranteeing that it was available. And so and that is the easiest version of this is, that we'll say Cloudflare operates a giant database. And whenever you create a certificate, you publish it to Cloudflare's database. And then my job, when I want to validate the certificate, is I go and look at Cloudflare's database. And you can obviously optimize that with Cloudflare signing, double signing it. Then your job as someone who has a domain name is to check Cloudflare's database occasionally and make sure that things in the database. This obviously requires trusting Cloudflare. And if Cloudflare decides to cheat, or the log, as we say, and if the log lies, that is the way the log lies is that when I, the relying party, go to check, it says, congratulations, here's the certificate. And when you, the origin, go to check, it says no, it doesn't exist. And so you don't see the surreptitious one, but the verifier does. And obviously that may be a little hard if it's a big lookup table, but if they're signing them, it's much easier. And so this is what this is a counter signature scheme. So I think that the design of CT was not a counter signature scheme initially. It was something else. It was what you call a zero trust scheme. And the way the zero trust scheme worked was effectively, I'm going to use the bad word, it put all the certificates on a blockchain, not like a conventional blockchain, but it's a signed chain of blocks. And the idea was that there was a Merkle tree is the technical term here, as David just said. And then the idea was that when you got a certificate issued, you would also get a proof that it was included in the Merkle tree that you could hand to people, they could validate. And then the relying parties had to somehow get the current state of the Merkle tree so they could basically validate they had the same Merkle tree state as everybody else. The Merkle tree gives you a compact summary of the state of the world. So the idea was there was supposed to be a compact summary that you could somehow learn, and then you'd have a chain of signatures or hashes that basically chained back to that compact summary. And so as long as you had an efficient way to deliver that proof and an efficient way to deliver the compact summary, they'd be good to go. So this is a very coherent design, and then runs into a piece of reality. And the piece of reality is that certificates are issued now on the timescale of seconds. And this whole compact issuance thing depends on basically folding a pile of certificates into one thing and gluing them all together and publishing that summary. Because in order to validate that the proof is okay, I've got to have the summary. So the thing we ran into is basically that you can't have both zero trust verification and immediate issuance in the same design that anybody knew how to do at the time, at least.
This is like uncannily like the Bitcoin problem, right? Or the transaction.
It's very similar to the Bitcoin problem, yeah.
Yeah.
And these are all the same kind of like physics invariants, right? And so the problem got solved basically by building in effectively a countersignature scheme. And the way the countersignature scheme works is the log promises that it will include, it gives you a receipt that says, I promise I will include this in the Merkle tree eventually.
Yep.
And that's enough to make the certificate valid at the time. But then the problem becomes basically, what if the log just lies? It doesn't include it.
Yep.
There's a whole bunch of
Right. So in the system, like in the original coherent system without countersignatures, all you have to trust is that the certificate authority is publishing their certs and like, driving the protocol, right? But in the countersignature system, you have two different entities that can now, be messing up, right? The CA or, in this countersignature, this promise in the future to include it in the next block or whatever, like the log could also lie at that point.
Yeah, I think the assumption in that case is the log and the CA are colluding, and the CA is misissuing, the log is lying about inclusion, right? And so in the original design, there was some unspecified but presumably strong mechanism where everyone had a group consensus about the state of the tree. And so as long as that mechanism was secure, then there was no way to basically have the split view where thing was apparently published but not published. But in this case, all that has to happen is the log has to lie. And so there's been a bunch of attempts kind of like to unwind that thing by a combination of like retroactively checking that things were in the log when they were supposed to be in the log. Eventually that included the log, or I think that's one thing. Chrome does some of that now.
Yeah. So like, and the thing we're talking about here is why we have SCTs as opposed to
exactly.
science.
Yeah, the receipt is the SCT.
And like, I feel like when I have discussions with people who are skeptical about the efficacy of certificate transparency, like people that are not super TLS literate, right? The gap that I tend to see is people not getting that like half of the system is, certificate authorities publishing and there being a log. And the other half is the browser is modified now to go check for some artifact of that signature. And the artifact of that signature is like, in a perfect world, the artifact would be a proof of the signature, right? Like something that rolls back to, the signed tree head or whatever, right? But in reality, what it is an SCT, which is a signature of a promise to include this, cert in the next block.
Precisely. Yeah. And so like, we've been digging deep here, but just unwind for a second, right? This is a big improvement. Like even in the countersignature scheme, it's a big improvement. It's a big improvement because now in order to cheat, so like the current log policies, like typically require, I can't remember if it's 2 or 3 different countersignatures in the 2 or 3 different SCTs. And so like now if you want to misissue, you got to like convince 2 other people who have no real financial interest in doing it to like lie about whether things have been included in the log, number 1. And that's pretty hard. And number 2 is a lot of sort of CA misbehavior is not like malice. It's just kind of like errors. Now, those errors are typically assigned, maybe things are wrong further down the chain. And those things, as long as you actually and those things like are brought out by CT effectively, I mean, almost even if you didn't have the SCTs, because things just end up in the log. And so we found a lot of problems. Well, the community, I haven't personally, has found a lot of problems in CA behavior just by log examination that, no one made any attempt to cover up. So this is like a big improvement. So I think this sort of, if one wants to offer a critique of like CT based on this kind of conversation, the critique would be that there's a lot of infrastructure in CT that like maybe you didn't actually need because you could have gotten away with a simpler scheme that had the similar security properties. That'd be the critique I'm sort of implicitly offering here. But I want to be clear that like this is actually adding quite a bit of value.
Oh, yeah.
And Chrome is auditing SCTs.
Yes.
So like, not only would you need to get multiple logs to lie, you would then need to block forever any Chrome from being able to run that audit and determine that SCT was not there. And then that same auditing goes back through the same sort of privacy infrastructure as safe browsing. To make it back to Google without revealing like your specific browsing history. And so
Absolutely.
like an unincorporated SCT will eventually be caught.
So like the Chrome audit process is interesting. Like one of you should rattle off how that works.
I mean, you should, David, since I'm sure you understand better than I do.
Yeah, David.
It was finished by Chris Thompson around the time that I joined, so I don't have the details down, but he did write a full paper about it that went out to, I want to say, Usenix or Oakland in 2022. But it uses the same hash dance thing that safe browsing uses. So if you're familiar with that, that's
absolutely.
how it goes through. I'm not super familiar with that, but that's how it like reports back. And then Chrome just tracks all of the SCTs that it sees, and then occasionally pulls down the component infrastructure in Chrome, is able to push down tree heads and then the individual browser clients can verify the SCT against the tree head, if I recall correctly.
Yeah, it feels like a problem that you keep running into with CT. Comes up elsewhere too, like with revocation, right? But a problem that you keep running into is like the simplest way to solve things is to have a browser go talk to something, right? Like, go post some bit of telemetry and then we'll drive off that, right? But you can't do that, right? Because what you're browsing to, like what things you're talking to is incredibly sensitive, right? So like you have this problem of like Google tracking this stuff, Google doing an audit of SCTs without giving it more telemetry about what people are talking to.
Yes, which is why we have all why there's a delay in determining like if a SCT was missed.
I mean, and that's actually, I think, maybe we talked about, the limits of like transport encryption a little bit earlier, right? I guess maybe an interesting pivot into like, TLS 1.3, iykyk, and all these things you see now, and ECH are all like decades old cryptographic technologies, right? I mean, like there's nothing in these systems that you couldn't have built, the minute you knew about Diffie-Hellman, and certainly the minute you know about Kurt Diffie-Hellman, right? And what started to happen over the past 5-10 years is, along with this revolution in how fast we can verify, is a revolution in how fast we can pull in new cryptographic technologies into the internet, right? And, if we put like the blockchain world aside, which has been incredibly fast about adopting things, the zero knowledge proof especially, things like that, right? What we're starting to see is a faster adoption of sophisticated technologies, things that are only a decade old into internet protocols. And so, blind signatures be a good example, VOPRFs are a good example, and you're starting to see those really integrated into modern protocols. Especially private relay, we were talking earlier, has some of the stuff in it, right? The sort of latest thing that we started seeing is all these new private data aggregation technologies, Prio and Poplar and things like that are now being standardized in IETF. So if I were to flog where I think the next frontier is private information retrieval, where we're just starting to see techniques for having efficient retrieval of data without telling the server what it is you're retrieving. And so the scheme you were alluding to earlier that the safe browsing uses is sort of like weak sauce private information retrieval, right? So like the cheapest private information retrieval scheme in the world is not cheapest, the obvious one is you just send me all the data and then I have it and then I like look it up in the database, right? And that's like not very efficient, but it's like naive, right? So the next most naive thing is what safe browsing does, which is basically you effectively bin the data into bins, and then I say, well, give me one of the bins, and then I get exactly the same situation, right? And as long as the bins are kind of sparse, then it works okay. But real PIR doesn't tell the server anything about the data you're retrieving, and we're just now starting to get to the point where we have like I wouldn't say efficient, but like maybe plausibly efficient for certain scenario PIR schemes, and we're just starting to see the point where people are starting to think about using them, and so I guess if I were to flog something, I'd say this is a place to watch.
Yeah.
It's interesting, right? Because when I think of PIR, I think about like Apple and Google, right? Like I think about like, that's a giant like forklift thing that they're doing in their infrastructure to like, make promises to customers about how they're tracking the data and all that, right? But the way you're thinking about it, the way, what I'm hearing from you is really if you can nail the PIR, like the cryptography and the basic, tech stack for PIR, like if you had that to begin with CT would look different.
Yes, it would.
Right? Yeah. Like it would be a simpler and probably a more coherent design if you just had that one little building block to build on.
I think I would remove a lot of the issues, because a lot of the issues that Dave was alluding to about CT are about how you basically get the current state of the tree, right? And we still have the latency issue, but that issue I think has like become less important over the years. And I think if you look at designs like Merkle tree search, they kind of just assume that latency isn't much a problem anymore, right? So I think there's a primitive that like we could use all over the place. I think that's I guess the what I'm hoping we're going to live in the next 10 years is a world in which because of the relationships that have been forged between the cryptographic community and the academic community and the protocol community, that instead we'll have a feedback loop where we say we like something, they say it was almost here, we play with it, and then it's like suddenly here, right?
Yeah, we should loop back onto the relationship between academic cryptography and standards group.
And as long as you don't ask for smaller post-quantum cryptography, they're fine with it.
I don't know why those guys won't do that. It's just like why don't they just try harder?
Nerd harder, cryptographers.
So, before we like run off the end of CT, I guess I have a couple of questions for you, right? This is obviously coming from a write-up that you did that kind of, picked an interesting fight with some of the Google people in a good way, like it was a positive thing. with, kind of the people working on this on Google side of things, right? So like we have this basic, like this layer of indirection that we've added with SCTs, which introduce all these weird problems and like, enable colluding and all that, right? But there's a window of time within which that matters, right? Like the fundamental problem that we're trying to solve is just, it takes too long to get a certificate fully included in the logs, right? And now we have Acme, like people just expect certificates to issue instantly, right? So like that's why that layer of indirection is there. But that's only meaningful for the time interval during which that's the case, right? So in theory, you could have a design where you have an SCT thing that then just gets like overruled. I guess I'm not thinking about this very carefully, right? But like, I'm wondering why servers can't just like, staple this.
Yeah,
right?
yeah.
Like, why,
well, I mean, David, I see you like twitching there. So you want to jump in?
Oh, well, I mean, I was just going to say, like, this goes back to it being 2014. Like, at the time, the idea of, like, I wasn't specifically there, but, like, the constraints around CT hitting the real world at the time was, shit, we're not going to be able to incorporate these things fast enough. So we're going to have to have a merge delay. So we're going to have SCTs. In practice, like, this just, like, isn't true. And it isn't true anymore. I don't know, like, how true it actually was. Like, whether this was something that we thought was true at the time because we were trying to, we thought there would be way more CT logs than there turned out to be, and that there would be less of a kind of heroic effort to run, right? There's like less than 10 CT logs in practice as opposed to something that like every CA runs. As well as like we thought, we're not going to be able to incorporate be able to give a response to a certificate fast enough without SCTs. And so immediate incorporation was kind of seeded in exchange for making this something that was actually deployable. But if you go and look at like Filippo's Sunlight logs, like it still has SCTs, but the SCT actually only exists after the certificate has been included in the log.
That's funny.
And so this was really just an artifact of like what the performance characteristics were at the time, versus like where we ended up with. And like one thing like I repeatedly find myself doing at Google is someone will come to like Chrome security and be like, I have a problem and I think it could be solved by a transparency log. And then we tell them not to use the PKI's transparency log. Then we tell them not to use SCTs. And then usually whatever their problem is, actually, they're like, there must be a different shape of a problem we can get where we don't need a transparency log, because like we've just been discussing, this whole space is pretty hard.
Yeah.
And so SCTs are really a artifact of a coherent design hitting the real world, and then the constraint being performance. Like at the time, we can't do this fast enough.
So like the thesis here is there was an original design with Merkle trees and a lot of mechanism that was sort of based on like a coherent idea of signatures being signed. And then we had this layer of indirection, which may or may not be required, right? We have this like counter signature scheme. Like the end of your like second post, it's awesome. We should have a link to it. It's a really good, like it really helped me kind of understand the dynamics of the system that I kind of just understood in the abstract before, right? So it feels like there's a take that you have that like there was a simpler design here, and it's obvious what that simpler design was, just like a pure kind of signature system. And I'm curious, because I don't have this all the dots connected in my head. What is that simpler system that you're talking about look like end to end?
Yeah.
Like if we just got rid of the mechanism you don't like.
Yeah. So I think there actually are, I guess I would say what we have now is an easy compromise between an attempted zero trust scheme and what is actually, that has a counter signature scheme hiding inside it. The counter signature scheme hiding inside it is throw away the Merkle trees and you just do SCTs and nothing else. No one bothers to audit that the logs are not misbehaving, and you just live with and the assumption is basically that getting three logs to lie is not a practical attack, right? That's the simple scheme hiding inside it, right?
You're just signing signatures, basically.
No, yeah, literally it's just SCT. It's exactly the same thing you have now, but no Merkle trees. And then when you want to audit, like that your name doesn't appear in the log, there's like something where you just like is a REST call and you just download all the certificates. There's no more.
Oh, this makes a lot of sense. So this is basically a stochastic pinky swear, right?
Yeah,
it's like a single pinky swear is not valuable because that person could lie. But if you get enough pinky swears, then like you're eventually asymptotically converging on something you can trust. And that's a really simple design.
Yeah, that's a simpler design. And I think that it is less good than the design that sort of David is talking about that actually has like validation. It is just simpler. And so I think, I have to admit, when I started writing this, I did not know Chrome was doing anything, because I sort of read that earlier paper that said Chrome did, is that they sort of looked at this and kind of given up. And so I think that like the property of Chrome scheme is interesting. I've been sort of struggling trying to figure out what the properties of Chrome scheme is, because in many respects it's actually trusting that Google isn't going to like lie about the context of the log.
But then it doesn't make any sense for Google to lie, right? Because they control Chrome.
Well,
to begin
no,
with.
sure enough. But then, why don't they just issue all the SCTs and we'll be done, right? I mean, I guess this is what I'm sort of saying is like that if what you're trying to do is a fully public verifiable system where nobody can lie, that's not what we have. And we have something intermediate between that because we have Google doing this, but like, does anybody else benefit from that? I'm not quite sure how, right? And so I think that the interesting question to ask, so I think there's like, no one I think is going back to countersignatures as the only thing. Like that's clearly not the way people want to play. I think the interesting question to ask is, given that some of the constraints that we were just talking about have been relaxed, that maybe you can sign much faster, maybe you can have local incorporation much faster, maybe we can find a way to look things up without having to like burn a bunch of like privacy budget. Is there a new design which meets the zero trust aspirations that CT had, but actually is simpler in some ways? And I think that you see groping towards that, but
this is like uncanny. So you've spent your whole career deeply engaged with the IETF, and with standards work and like shepherding things like this, right? So like, and I've spent my whole career throwing stones at that process and not being involved with it, right? But it's just like, it's uncanny how, so this is a successful design, right? Like we're, for one thing, like the gap between the original coherent design and the model that kind of emerged that you're talking about in your post and all that, right? It's potentially closing anyways, just because technology is getting better and like the new CT logs will be able to do like, quick merges and things like that, right? But like the exact same kind of phenomenon with like, we had a service model and the service model wasn't quite right. And it was designed around like the technology that we had available to us at the time. But then because the IETF and because the industry really takes so long to put things in the field, like that the landscape is different by the time it meets reality. You're talking about DNSSEC, right? Like this is exactly the same thing that happened with DNSSEC,
that's so
right?
amazing.
So like here with CT, it's just like, it's the SCT model versus direct signature stuff or the privacy aspects of it or whatever. And like in DNSSEC, it's like online signer, right? It's like, are we building a protocol that like where the servers can actually do cryptography on the fly, or because it's 1995, you can't really expect anybody to run like any kind of encryption algorithm on demand because it's too slow, right? But it's the same thing where like a lot of the incoherence and the weirdness of the protocol when it hits the real world is that phenomena. It just keeps happening inside the IETF.
Well, I do want to briefly defend the IETF on the CT front, in that all those compromises were actually made by the original CT team and not by the IETF. The IETF CT version is every bit as good or every bit as bad as the original CT like submission. So like, while the IETF has bungled many things, it didn't bungle that one.
It's difficult, the interaction between browsers and CAs, whether or not it's the CA browser forum or the IETF is involved, is simply an inherently very complicated dynamic for several reasons. And so SCTs were an outcome of responding to CA's concerns that they needed to be able to do effectively immediate issuance.
Yeah, I think I love this DNSSEC segue though. I think that's a great segue. I think you may be a little bit being too generous. There definitely was. I mean, the question to ask always in retrospect when you have these designs is how many of the constraints were real and how many constraints were imagined, right? And it really was true that like digital signatures were like incredibly slow and like painful to do online. And then there's also like this thing about how we didn't want to have the keys like online in the devices because reasons, right? And I think that was much more of an imagined constraint than a real constraint.
I feel like you need to do that to use them to sign things.
Yeah, so like I want to be careful about how I dunk on standards processes in general, and I should also generalize, right? Like my my moral enemy is standards processes, and not the IETF per se. IETF, I'm sure, is one of the better ones, right? But like the funny thing about that is, it's true that like in the original DNS, in the original DNSX, standardization stuff, like some of those concerns were real at the time, right? But you didn't get it anyways. Right? Like the benefit that you were going to get from offline signatures, from offloading the cryptography from like the hot path of the protocol, right? Like it didn't get deployed. So that by the time it did get deployed, that no longer made any sense. And it contorted the whole design of this thing. Like every problem got drastically harder because of this one constraint that you put in. Because like, I don't know, like it just seems like, and again, I think it's a shared thing with the industry and with, the standards groups. I also think it's real easy for me to say this stuff. But like yeah, it's like you couldn't look 10 years into the future and see what this is going to actually look like by the time it actually gets deployed. And we were talking earlier about like the lag it takes for standards to get done, like saying like quick as 5 years. That sounds fast to us, right? So it's like, if you kind of go into this expecting that, it's not going to be widely deployed for 10 years anyways, and that's where you should be looking.
Agreed. I wish I had it out because I have this talk that is going to turn into a newsletter, probably more than one newsletter post actually, about how to design protocols that get deployed, based on my experience both succeeding and failing at that. And the frame for this is actually the alternate reality where instead of TLS and the web PKI and, quick and whatever, what we instead have is DNSSEC and IPsec, and everything runs over DNSSEC. And DNS, everything runs over IPsec. And that obviously is not the reality we find ourselves in. And like, how do we get into like Earth 1? And I think that like the argument you made that's actually a more sane, coherent design than the sort of the giant mess of things we have now, like that is like fixes on fixes on fixes, right? But then you just see there was not a path to get to where that there from here. And my sense is a lot of things we learned is don't design in a vacuum, right? And I think a lot of those designs were done in a vacuum. And if you look at the, look at the CT design or the Quick design or the WebRTC design or the H2 design, those designs were done in collaboration with people who had real deployment incentives and really were going to try them really early. And so you got if there was feedback to say the thing wasn't going to work, you got that feedback early and then you had to respond to it. And my sense is, if you look at like TLS 1.2 when we did it, like we designed that entire thing like without anybody, there were no implementations, like we just papered it, right? And it took years for people to implement it. And if you look at 1.3, we had implementations like from the very beginning, basically, even when it was basically just, barely existing drafts. And so I think that DNSSEC design was built onto these type of assumptions that people just didn't understand weren't right. And because they had to make contact with the enemy, they couldn't tell. The other thing I think that you're being a little too nice about actually is, that in the world where you do have something like the web PKI, the actual value proposition of DNSSEC is quite weak. Like even if they did what it's supposed to do, if I lie about the IP address, but the person can't get a certificate, it's basically an attack. Basically, it's just like stops them from connecting at all, but it doesn't let them impersonate the server, right? So when you go back and you say that, you say like, well, why do I have all this apparatus that only provides you a very small amount of value when the real problem is, the confidentiality of the DNS connection more than the integrity.
Right. Obviously, I think all of us in this conversation are aware of, my take on DNSSEC, right? Because I'm very noisy about it. But like, I'm kind of stipulating, like just stipulate that it's solving a problem that's worth solving, right? And actually, when you talk about Dane, you're closer to a thing where there's a live conversation to have about like, whether that's a real thing, right? But I'm still kind of stuck on just a fundamental, like, it's the outcome of the design itself, right? Assume that the problem statement is good and like where you landed with DNSSEC is messed up in a bunch of ways, right? So it's like, there are reasons why it's not like deployable. And we're talking, for instance, about all this, this stuff that we're running into with the design for certificate transparency, solving the problem of, attackers can suborn the central authorities that issue certificates, right? And the reality is that the overwhelming majority of DNSSEC signatures are also centralized, right? They're done by registrars or whatever, right? So you have the same problem there. And like, if you bring that up in an argument with somebody who supports DNSSEC, right? Like the answer they'll give you is, well, we're just going to make, certificate transparency for DNSSEC, right? And for a lot of reasons, maybe I'm wrong about this, but I'm going to say this confidently. For a lot of reasons, that's not going to happen. Right? Like you don't have any of the incentives to get that worked out. But also you're going to run into the same problems that CT is running into, and they're harder to solve in the DNS context.
Can we review how DNSSEC works and how Dane works and why we're all groaning at the thought of transparency logs for DNSSEC?
Well, I mean, it's also possible that Eric disagrees with me. So.
I think I mostly agree with you. So like the DNS is a hierarchical system, right? So if you have, if everything starts with dot, and then dot, owns all the names under it, and they assign who gets com, and then com assigns who gets example.com. And if you were to have like, monkey.example.com, that they would assign who got example.com and assign who got monkey, right? And so what DNSSEC is like the dead obvious thing, which is that though each of those assignments is signed. And the assignment is obviously like effectively a certificate. It's a signature over the name and it's got a key, right? And there's like a giant amount of like bananas infrastructure to wedge this into DNS when it never intended to go in. From like an era, frankly, when people didn't really know how to design protocols that like were extensible. And so like you really had to force fit things into it. I'm not sure we know how to design them extensible now, but like we've learned some things about how to design them extensible. And then at the very end of it, like you have a bunch of records associated with example.com or whatever it is, the leaf node, and you sign all those records, right? And so that's like a very straightforward kind of design, modulo all the deployment problems Thomas is mentioning, right? And so the natural thing to say once you have that is, well, why doesn't one of the records that I put in there just be the public key of the server? And then I wouldn't need the web PKI at all because it's the public key of the server. And so what Dane is, and it's like, that was like people had in their heads, I think, at the very beginning, right? And then by the time that like, there was like substantial DNS deployment, I guess for some value substantial. And we had like massive web PKI deployment. And so it wasn't really like, and so then they were confronted with like the situation of the world as they found it, as opposed to the world in which you ideally wanted it. And they were like, well, what we're going to do. And so I think if you read the indictment of the DNSSEC people would make of the web PKI is it has two big problems. One of them is that, as you were alluding to, Thomas, there's too insecure. That there are a zillion, they would say, certificate authorities, and any single one of them can issue a fake certificate. And the second is that it's too expensive and too high friction, which is to say that you had to pay the CAs for certificates.
Point of order, a third thing they would bring up is X509.
Oh, true enough. I always find these like arguments about spelling to be quite tedious. All protocol encodings are awful.
Yeah, it's funny how big a deal it is if you go read like the working group stuff. Like one of the big enemies there is, kind of the DERization of IETF. Like it's culturally foreign, right?
Oh,
so
yeah.
It's like one thing we want to do is like push this out and get something that's like a more, IETF-y kind of design. But I'm also scrambling the point you're making.
Yeah.
Like the fundamental issues, right? Like issues anybody would bring. If you're going to be especially fair to the Dane people, right? The Dane people, that sounded bad, but whatever. If you're going to be fair to the argument here, right? Like things anybody would point out about the web PKI. One, too many issuers, no way to trust it, right? And two, it's expensive, or was at the time when Dane was like a big thing. It's expensive to do it.
And these are both like legitimate points. Like I want to concede these points like right off the bat, right? And
at the
time.
Now you can get all the free CA signatures you want.
And so I think like this is just like a great example of path dependency on the internet, right? Which is that when faced with these realities, there were two approaches you could have made. Two approaches you could have had. One is let us burn the thing down and start from scratch. And the other is how do we add a new patch, which kind of like makes the system really better in these directions. And so basically the two patches that are reflected in on the web PKI they are made about the same time as Dane are certificate transparency and let's encrypt. Certificate transparency to solve this too many issues problem, at least largely solve it, and let's encrypt to solve the free problem. And like, again, I think there's a fair case to be made. These are not as elegant designs as like the top-down issuance, but the great thing is they're incrementally deployable. And I think, CT obviously so. Let's encrypt was designed from the very beginning to be incrementally deployable by like getting a counter signature from an existing CA, which is the only way to roll out a new CA. And so what Dane is so to circle back, what Dane is not quite the obvious thing. What Dane is sort of partly the obvious thing and partly not. It's basically has like conceptually two modes. One mode is here is a signature over a hash of like a certificate or which ordinarily would not validate up to one of your trust anchors, but usually anyway, because I've signed it with my domain name, the key across my domain name. And the other version of this is here is the hash of a certificate, which must appear in the chain, but it also must be valid according to the web PKI. So like one version of this is kind of like pinning effectively, which is to say, here's a list of CAs which you must use, or keys you must use. And the other version is to say like, and that's designed to solve the too many CAs problem. And the other version is here is the thing which must appear in the chain, but don't even worry about if it's CA valid. That's designed to solve the free problem. And neither of these, unfortunately, has like quite as compelling a value proposition as you might like. It's obvious, I think. I think it's easiest to reason about the free one, which is to say that, say you in fact are tired of paying off the CAs to have your certificate, and for some reason you can't use LE, or you think this is before LE, right? So you say, great, I will get this Dane thing. Now the problem you now run into is that your web server needs to work with every web browser in the world. And many of those web browsers do not support Dane. And until the time when every web browser supports Dane, you still have to pay off the CA and get a certificate. And so you get no incremental value from doing this like for years and years and years to come, right? So I think that basically is a fatal flaw in any of these sort of free versions. And it was like something which when like Let's Encrypt was founded, like we took great pain not to create the situation for people that Let's Encrypt was a value from day zero, right?
Yeah. This is Adam Langley's like big argument about Dane and browsers and all that is like, it doesn't bring you from 1 million CAs down to 1. It brings you, to 1,000,001.
Yeah.
Because you're never gonna get to the point where you can just run Dane.
Right.
Yeah, I think, the time when you were like in permanent Dane is like very, very far in the future. This pinning thing, I think like you could argue has a little more value. It's just very hard to like actually persuade people it's worth enough to do all this heavy lifting against the backdrop of CT already existing, right? And against the backdrop, frankly, of any misconfiguration in your DNSSEC causes like your site to become unreachable. And so now it's like, really, I want to I'm going to marginally decrease my risk surface area by making my site potentially unreachable if I screw up. I mean, I will mention this is all kind of a tragedy because, if we had DNSSEC, lots of cool things you could do with DNSSEC, and I'll just give you one, which is you could shave off a round trip from like from your TLS connections because you could put the public key of the server in the DNS, and then you can encrypt directly to it from second 0. But you can't because the DNS doesn't work. Now, I mean, could we like sneak around and like have a web PKI signed and whatever? Like maybe that might potentially work. So like things you could do. Another thing you could do is you could like delegate. You could delegate my domain to other domains. And so like right now, think about it, right? You say like, oh, you want to have your like site hosted on a CDN. How does that actually work? Well, the way that actually works is that you put in a CNAME record, which says example.com goes to like fastly.com or amazon.com, right? And then amazon.com has to have a certificate for your domain name, not for amazon.com, because no one can trust the CNAME records because of the DNS. But if you trust the DNSSEC, then those would be secure and you have a different scenario. And so like, none of these are like, the greatest feature in the world, but like we are constantly fighting with like the insecurity of the DNS and not doing things we otherwise would do because the DNS is insecure. But there's just no incremental deployment path from where we are now to there that actually provides value all along the chain to get us there.
Can I interest you in a 1.5 kilobyte size signature for your DNS?
Well, exactly.
Your post-quantum secure DNS.
Well, we haven't even talked about that.
2.5 kilobytes.
Yeah.
Oh, yeah.
Well, we haven't even talked about this, right? But there is quite a bit of DNSSEC validation on the internet. It almost nearly all happens at recursive resolvers. So the way DNS works, that DNS gives you a bunch of records which end up on your machine, but almost nobody talks to the DNS servers themselves. They talk to some local server, which is called a recursive resolver, which does all the DNS resolution for you of traversing down the hierarchy. And lots of recursive resolvers do DNSSEC validation. So far, so good on that, but that doesn't get as far as the client. And so the client, but all these features we're talking about require the client to validate, not the recursive resolver to validate, because otherwise recursive resolver can just lie to you. And that's no good because the recursive resolver in many cases is provided by the airplane that you're sitting on. Why do you trust those people? And every time anyone has like tried to seriously study the question of whether or not you can actually retrieve all the signatures all the way from like the original thing down to the client, the answers come out really bad. Adam Lange did something about this like quite a while ago when I was back when I was at Mozilla. We studied this a little bit and like the answers were just catastrophically bad. And it wouldn't be any better, by the way, if you had 2.5 kilobyte signatures.
I can imagine, let alone the fact that I don't think, like, what's the actual uptake of elliptic curve signatures in DNSSEC? I think it's quite, they're really poor parameter sizes. I think they're like P192 or something like that. Like just migrating to more modern cryptography has been extremely slow. And now we want to replace that modern, air quotes, cryptography with possibly PQ stuff. So I'm not holding my breath.
I think like in terms of path dependency and incremental rollout and counter signatures, there's actually like a link there that like the problem of how do you roll out Let's Encrypt? How do you roll out Dane? How do you roll out, well, if you wanted to do a counter signature scheme instead of CT, like you end up in these like some clients are going to want to trust different things. So like the obvious failure mode for a counter signature is like, okay, so web browser A says, oh, we'll just do a simpler version of CT where a root program for browser A will just countersign. And then browser B says, fuck you, browser A. I don't trust your signatures. I'm also going to countersign. And it's like right now, you kind of end up in this world where everyone would have to pick which counter signature they were going to accept, or you'd have to send like one signature per root program on every connection. Similarly, like you can't start a new CA without like getting trusted in advance either by being countersigned by someone else, because there like is no way to kind of indicate what it is that you trust within TLS and within like the protocols that we have on the internet, which is both good and bad as like a symptom of the path dependence, I think.
Yeah, no, I don't think like a variant of CT that was counter signature only is like a viable story now. I think maybe if we like have a time machine it is, but like now it's too late. And like the same reason why I think going back to X509, the same reason we're carrying all this X509 baggage around is because like it's too hard to change and it's easier to just ignore it, right? If you go back to TLS 1.3, right? Like TLS 1.3 literally has mechanism in it that's designed to make it look like TLS 1.2. Solely because there were devices on the internet which freaked out if you tried to send them things that like look too different. And there's like literally a feature in TLS 1.3 co-designed by I think Kyle Nekritz from Facebook and a bunch of people from Chrome that basically is making TLS 1.3 look like TLS 1.2 session resumption. And because the Chrome guys discovered that there were too many errors from the middle boxes, and Nekritz was like, well, why don't we just make it look like resumption? And everyone kind of was like, lol, right? And that's what we did.
My claim to fame is I taught Kyle Nekritz at Michigan.
All right.
And then I was still at Michigan when he fixed TLS 1.3. I hadn't finished my PhD yet.
Okay. Before we switch out to another thing, like we talked a little bit about these post-quantum signatures are too damn large. And we talk a lot about how that affects, well, the people who are working on this sort of thing in TLS. And, David occasionally will ask me, like, are you sure there aren't any smaller fucking PQ signatures? And I'm like, there's one. And they're ghosting us all. And, everyone's got their hands bit by Psych and SADH being killed. But we're thinking about how do we upgrade TLS 1.3 handshakes with all like 5 or 6 signatures in a handshake, including these SET signatures. But also, like, how do these big effing signatures and public keys affect actual operation of CT logs? If the answer is just literally they are slower again, are we finding ourselves back to something closer to when CT was originally rolled out, which is like we thought it would take longer to get these into the log. Therefore, we have SCTs and not just here it is in the log, go look it up immediately. Or is that just sort of like, we'll deal with it. We'll just hash faster or something like that.
Yeah, I think actually David probably understands better than I do. Happy to riff on it.
In my experience, if you imply you're going to delay a post-quantum transition until the cryptographic options get better, a variety of cryptographers will get mad at you in real life. But I think that is an interesting question that I've been thinking out a lot recently about, like, how hard should we try to rework the PKI to both get better requirements, like get the properties that we want better while simultaneously, making, achieving post-quantum and sacrificing, some amount of something else probably, versus, can we just sit back and wait and maybe the options will look better by the time we're deploying this anyway, especially if we focus on like kind of the migration aspects of it before the specifically what it is we're migrating to.
I mean, I feel like there are sort of 3 angles people have kind of taken on this. One is bite the bullet and just be like, oh, we're just going to like cross out EC and write like MLDS everywhere and like everything will suck and be slow. The second is, I think the one you just alluded to, which is like, watchful waiting and say like, let's just cross our fingers crossed and hope like it won't, hope it won't get too bad before like someone gets a better algorithm. And then the third is like, do like some real radical surgery kind of stories, right? Which I think is the bucket that off-chem kind of falls into, and maybe maybe Merkle's research. So I'm not sure Merkle's research like definitely has more of an incremental deployment kind of like flavor than off-chem does. And I think Dennis Jackson's what does he call it? Like about the compressing intermediates by just removing
abridged certificates.
There it is, yes. Falls more into like the first kind of like into kind of like the paving the way kind of category, right? For version 2. And I mean, my fear, honestly, not a fear, but like my sense is this is like, even with everything we know how to do that is clever, like the post-quantum search are going to be so grim that like we're not going to get much in the way of deployment, like with the current state of algorithms. Like even if we went all the way to Merkle tree search and a bridge search and everything, are people really going to suck up, MLDSA in the system? And if the answer is, and it's one thing to be like, Google and Facebook and some other people have some MLDSA certs, and if you like, and like a 1% of connections, they agree to negotiate them. And it's quite another to be like, basically everybody in the world has an MLDSA cert. And,
Right.
The security properties of the signature thing are really different from the security properties of the key exchange thing, which is to say that, if you and I do MLChem, then like we are protected and we don't really care what anybody else does. But in order for you, the server, to get benefit from having MLDSA, you need me, the client, to refuse to trust an ECC certificate from you, right? And so like in the sort of like big version of that, the clients can't do that until basically everybody in the world has an MLDSA cert. In the smaller version, and I had some like hand waving about this in a recent newsletter post, maybe there's some way for sites to be like, well, maybe you generally would trust an ECC certificate, but for me, I want you to like only do MLChem, right? As you get some value incrementally. Yeah.
Or MLDSA, yeah.
Yeah, but at the end of the day, my sense is like with the current state of play, we'd be lucky to see, 10% deployment penetration in the next 5 or 10 years. And then the question is, how much does that move the ball forward? In the world where suddenly we have a post-quantum computer, how much does that actually accelerate the transition versus just starting the minute the post-quantum computer is released? I don't think anybody knows, right? Because I mean, the day if that happens, suddenly a bunch of unpalatable alternatives start to look a lot more palatable. And suddenly it is like, well, I guess we do have to absorb 10 kilobytes of certificates because it's that or nothing. Where nobody does that now.
Yeah. I think having, at least in anyone that has to interface with the US government, having FIPS compliance and anything else that needs to be like sold to the US government is really pushing at least support, if not adoption, for this stuff. And in my opinion, if we have at least support for these things, we'll be in a better place. But of course, like with signatures, it's less of a urgency against an adversary, so much as we know it takes so long to get the ecosystem to update to anything. So trying to get something working now so that you can at least have the option of like an MLDSA certificate supported in TLS 1.3 and so on and so on and so on, and validated by a client. Just having that available will, I think, assuage a lot of people, even if it's going to be like, I don't doubt 5 to 10 years for significant adoption is probably optimistic.
Well, I think in the absence of more thrust, right? I mean, the problem is it's just not like a high priority for anybody because like the algorithms are bad and we're not going to see much deployment anyway. So it's kind of like, I mean, that's key exchange thing is a high priority for people when they're pushing it, right?
Yes, exactly. Yep. And like that's the hybrid chem is supported by Chrome and Cloudflare. And I think Cloudflare is already reporting 13% of their negotiations are using that hybrid chem, which is amazing. It's only been out for a couple of weeks and it's already at 13% of, I think, of their TLS 1.3 connections or whatever they said. That's amazing. So that's very good. And like, we can afford that. If it definitely helps that MLChem is, not that much bigger. It's about the same size as, say, your RSA or something like that, or big things like that in your key agreement, in your handshake. For signatures, it's smushy. I don't know.
I mean, you're much more tuned into this world than I am. Do you have some sense that like there's stuff on the horizon? Do we have hope?
This is what's really frustrating for me, because we do have hope in the one isogeny-based signature scheme that is part of the NIST post-quantum on-ramp for signatures, because there's like 40 other signature schemes, because they're like, we want something that's not lattices and we want smaller, please. SkiSign is extremely competitive there, but the community of isogeny cryptographers that contribute to SkiSign are just kind of floating out there. They didn't show up to the latest NIST meeting, and like 39 other signature scheme teams did, including Mayo and UOV, like these other schemes that are not they're based on multivariate or whatever, that are competitive in their own way, either very small signatures and huge keys that make them more appropriate for different parts of TLS, blah, blah, blah. I honestly think that ski sign would like hit the sweet spot of all these axes of small signatures, small key, decent enough performance to make everybody happy. But I don't know where the ski sign people are.
Well, the ski sign on paper needs a 10,000x performance increase on signing to be
the latest.
Yeah, that sounds more reasonable to me than just like coming up with like, you know, new math, right? Like we're a lot better at computers than we are at new math.
The latest implementation rumors I heard is like 2 milliseconds or something like that. It's definitely within the realm of competitive, and it's like they're not out there. They're not aligned and pushing ski sign, and I think they're missing an opportunity, and we're all so I don't know. I keep sort of needling people and be like, hey, what's going on here, what's going on, and just everyone's kind of going off in their own corner doing other isogeny stuff, I guess.
UOV is a particularly interesting kind of point in the design space because it has signatures of size in between an elliptic curve and RSA, 128 bytes, but it has 66 kilobyte public keys. But that's actually like fine for pre-distributed keys that aren't that big. So you're not going to be seeing a root store of UOV keys where there's like 100, 200, 300 keys.
And the math is attractive.
But you could see a CT log list of UOV keys where there's only like 5 to 10 of them.
Yeah.
And it's based on an NP hard problem, I believe, which is like actually somewhat novel for cryptography.
Yeah. The math is nice to implement, and it's also pretty, like, it's just kind of stood the test of time. So it'll be interesting, and there's probably time between now and, you know, I don't know, D-Day, Q-Day, whatever.
So how did you feel when, like, for a moment we were all worried that actually there was a good attack on lattices?
I was looking at it, and I was taking the authors on their word that this will affect basically all lattice constructions more fancy and more complicated than signatures and key agreement. That the ratio of the Q to the, you know, the size of the, you know, whatever, if it's close, you don't have enough room to leverage an attack, which is the case for MLChem and MLDSA and Falcon-ish thing. That's basically the non-fancy shit. Other fancy shit like anonymous credentials, fully homomorphic encryption, which is, you know, a lot of the things that would have put post-quantum public-private information retrieval on notice would all be just completely blown away. And if that were the case, it would basically be like, we still have a ton of cryptography out in the world. Like a lot of the private relay stuff uses things that are basically blind signatures in one way and anonymous credentials in another way. Trying to find a post-quantum version of any of the more fancy crypto pretty much was all relying on fancy lattice settings. And it was just sort of like, well, fuck. Like, we have no ideas of how to do any of the fancy stuff without lattices. Like, there might be a couple of solutions, but they're incredibly not scalable and performant and adoptable. So that was where I was going to be, which is like, this is going to make people trust in lattices less. It might slow adoption, but honestly, we would still have MLDSA and Falcon and MLChem. And then 2 weeks later, 2 independent researchers were like, we found a bug in the algorithm. And the researchers said, nope, this is broken. Like, my algorithm does not work. So that was a big phew. But people are still looking at the thing and trying to be like, okay, maybe this part was broken, but there are some interesting ideas here, and there's like a leap here that we want to understand fully. And so we don't really know the blast radius yet of the paper, even if the specific algorithm it was proposing against, lattices is considered broken and not real. Oh, not good. And like, this completely motivates why NIST is like, cool, we have 3 post-quantum signatures based on lattices. We have some older ones, post-quantum schemes based on lattices. We have some older ones based on hashes that like we've trusted for a long time, but are only usable for certain scenarios. That's Sphinx and XMSS or whatever. We want something else, not necessarily based on lattices. We don't want to put all our eggs in one basket, and we can't use these hash-based ones for TLS, for example. So this underlies that precisely.
So what do you think we do if none of this works? So what do we do if someone like describes a post-quantum algorithm for breaking all of this fancy stuff? Quantum algorithms. Like, so we have a quantum computer and like we have no cryptography at all.
Global Kerberos.
Yeah, exactly. Yeah,
Yes, Kerberos.
Yeah, go talk to Adam Langley about that. Enough cryptographers in my world are basically like, I don't think we live in that. Is it like mini crypt or the other, algorithmic complexity world? I forget what they all are and the differences between them, but I do like, it's basically arguing that one-way functions do not exist or something like that.
Mini crypt is no one-way functions,
okay.
But you still have like symmetric crypto. So it's no secret. It's only secret key crypto. It's no public key crypto.
Yeah. Okay, cool. I don't think that's true. I do not think that there will be one quantum algorithm that will kill all of the schemes that we think are, at least right now, post-quantum secure, because they are based on very diverse problems. You've got your codes, you've got your multivariate, you've got your lattices, you do have your isogenies, and you've got your hashes. Literally, worst comes to worst, we literally have to tell everyone, like, cool, you've got your stateless hash-based signatures. We're going to teach you how to use them. And it's going to suck, but we will have them. And so there's at the very least that. But I do not think that we'll actually end up in the all you get is hash-based signatures world.
And what, Merkle puzzle boxes for key exchange?
Yeah, or something like that. But it's really tricky because we have like these teeny tiny quantum computers and we don't have like higher level. I mean, there's lots of people working on this. Like, so when someone puts out a paper that's like 60 pages long and says like, yes, I've broken all the lattices modulo, like the simplest possible constructions, it takes like the whole world staring at this paper, the whole cryptographic world staring at this paper for like 2 weeks, because only like 10 of them know quantum computing and quantum algorithms and lattice cryptography enough to like basically know what this paper is arguing and then tell you whether it's correct or not, or there's a bug or not. And like part of that is we literally don't have real quantum computers. That's why we're planning to roll this out yet, because we're not there yet and blah, blah, blah. But it's really hard to falsify anything. Like with a classical attack algorithm or attack algorithm that can run on a classical computer, you just go implement it and you just try and run it. And if it doesn't quite get there, you throw more computer at it and see if it'll work. And you can just try it. And we can't really do that with quantum algorithms yet. And we're in this hazy space that's unfortunate. Okay.
There's also very little mathematical cryptanalysis in the United States as an artifact of how the university system works here. In the US, cryptography is usually in the computer science school.
That's also true.
In Europe, cryptography is often in the math department. And math departments in the United States often do internships. If you do number theory and you are in a math department in the United States, there's a good chance that you at some point have done an internship with the NSA, which then prohibits you from working on a variety of topics. And so just like structurally, you end up with not a lot of people doing mathematical cryptanalysis in the US, let alone quantum mathematical cryptanalysis.
Yep. It's annoying. And we want to talk to Nadia more about that sort of thing in the future, I think. Okay. To do a hard 180, I don't know about 180, but like away from post-quantum and back to transparency. So we've had certificate transparency, which is signatures over signatures, whether it's in the Merkle tree, which is what we've deployed, or not, which is arguably what we should be deploying now. And we have key transparency, which is basically all these messengers that are end-to-end encrypted are deploying, unfortunately, besides Signal, but I hope they will get there. For your WhatsApps and your Facebook messengers, they're deploying large-scale key transparency that uses more complicated cryptography in there to help audit it and check proofs and get a little bit more privacy, I think, about like what's in the log so that people can't just like get people's phone number for random queries and get all their public keys and stuff like that. They have a little bit other stuff in there. People have been talking about binary transparency for a bit, and I am only aware of Android having binary transparency for the Android OS. Yeah,
sounds right.
Yeah. Do you have thoughts about binary transparency? And like, do we have a way to deploy simpler, nicer to run binary transparency without all these Merkle trees that gets us where we want to go? Or is it like, nah, it's a different security model?
I was like really bullish on this for a while, and then no one seems to make much progress on it besides Android, and I'm not quite sure why. I know why we didn't make much progress on it when I was at Mozilla, which is just kind of like lack of thrust. It's like maybe it's worth stepping back and saying what is the nominal security guarantee that BT provides, right? And it's sort of related to the CT guarantee. And the nominal BT guarantee, so I think if you take a step back, you say like, so you got like some source code, and the source code gets compiled into binaries, and the binaries get distributed to people, right? And so what BT does is it at least nominally ensures that the total set of binaries which are possible to run in your computer for a given application, whatever that application operating system, whatever, is known to the world. And in the simplest version, it's merely the cardinality of those is known, namely that there is a set of them and there's no more than n, right? And so, so the attack that BT concerns itself with is that some attacker who controls the update channel in your computer, like for instance the vendor, is unable to substitute a malicious binary for a non-malicious binary, right? And I think it's pretty unclear exactly what value this provides, except in like relatively narrow circumstances, which is to say, there's like a lot of stuff on your computer, and if the vendor is trying to be malicious, why do they have to make a different binary? Why can't they just like make a binary that is like vulnerable? So it's not clear to me what BT alone provides in terms of security. I think what BT is intended to be, what I used to talk about this, is as part of a broader ecosystem that includes reproducible builds in the open source. Yeah. And then the story becomes much more straightforward, and the story becomes, look, the source code is public. You can verify for yourself that you can verify for yourself, or someone can, and you actually can't because it's too much work, that this source code compiles down to a given binary. Here is a list of all the binaries that like anybody could possibly install, and you can map each one of those to source code in the blockchain, right? And so then the theory becomes, at least in theory, that someone had an opportunity to review the source code and verify the source code was non-malicious, and therefore you can convince yourself all the way down the chain that you haven't had a substituted binary that was bogus, right? I think that is a somewhat more plausible security story. I say somewhat more plausible in the sense that like any modern piece of software is like full of vulnerabilities. And finding them by inspection of the source code is incredibly difficult. And so say you persuade yourself that like this is like a legitimate copy of Firefox or Chrome, the next version of Firefox or Chrome is going to disclose like pile of vulnerabilities that were already in that version of Firefox or Chrome. Like every release of one of these products has like a list of like all like the memory vulnerabilities that were in the previous version that were all there and nobody found before you this minute. So it's clearly the case. So it's not clear like what a great set of security guarantees it provides. I think this is particularly weak in cases where you have like an end-to-end system which is completely controlled by the vendor, where like you can't see the source code, then it's just the whole thing kind of falls apart. And I think if circle back, you probably remember when Apple had this stuff that was supposed to be about CSAM detection for stuff included in iCloud, and they went to quite a bit of effort to demonstrate that like you can convince yourself that the list of hashes that they were checking against was a valid list. And I was like, Apple controls the entire stack top to bottom. If you don't trust Apple to lie about this, why do you trust anything they're saying, right? So I do like worry about, more and more software now has a property that basically vendors can auto update anytime they please. And I do worry about the vendor's ability to auto update with malicious binaries. The question of auto update with customized malicious binaries, which is really what BT is intended to prevent, I think is a sort of weaker kind of threat model. So I guess I was pretty enthusiastic about this for a while, and I still think it'd be good, but I think it's sort of lower on the my stack of priorities than it used to be. And just to go back to I think even circle back to what you were saying, David, about people want to use a CT log for thing. When we first looked at this, I think it was Richard Barnes was like, well, we don't want to stand up a whole new log. So what we're going to do, we're going to basically get a certificate that is called like hash of binary.bt.mozilla.com, and then we'll just get that issue with LE, and then that'll be in the CT logs. You can look at the CT log, and you can verify the whole chain. So it's just have a new log. So we never actually did this, as far as I could tell. Except maybe found like a test or two, but that was like the level of of kludginess people were getting excited about back then.
Yeah. But now you're giving me too many ideas of I could just shove things in these CT logs and they'll just do all the work for me. I don't need, if all you want is like signatures of signatures, basically, or whatever. That's interesting because some of the threat metal is literally like, do you trust the vendor, either the OS vendor or like an application vendor, to give you the right one? But I'm also sort of thinking of like, if you're in a network, for example, and someone is tampering with the downloads you get to upgrade your OS or upgrade your application. There's other ways to do transparency that basically involve gossip. It's sort of like having your own, like, I've seen these binaries, or I've seen these keys, for example, if you're gossiping the keys that you've seen and you like vouch for them of like, I see them over here, and you gossip it to your friends or anyone you connect to. And if your, local network is serving you a very suspicious like version or hash of a binary, or patch update that no one else sees or isn't present in the binary transparency log, you go, don't do that. Or, the application in theory would be like, checking these gossip logs or checking the transparency log and say, we're just not going to apply this update, and we're going to notify you that we're not updating. Maybe go to your home network before you update or something
hopefully
like that.
The updates are signed, right? So the trivial attacks shouldn't be possible.
Right, exactly.
I mean, I'm not sure how many people actually sign their updates, but they should.
Yeah, they should.
Though that, of course, creates a new problem of like managing those keys, which is like can be like which could be like quite an operational problem for a smaller shop.
Yeah, but I think it's like there's that sort of, how much do you worry about that sort of attack model versus the literally what you just said, which is like software is full of vulnerabilities. Even like highly resourced teams with very we understand how important it is to have these piles of software to be secure. I think Chrome patched a 0 day in the wild just recently. It's hard to write secure software. So why would a attacker go through all the effort of like getting in the way of what downloads you're getting and serving you a bad one, and then like possibly ticking off, like if you don't have transparency, maybe it wouldn't detect it, but also like they could do something undetectable and literally like leverage a 0 day. And the answer to that is, well, sometimes those things are more expensive to do and require more skill than literally just like doing a network block and just like making sure that everyone who's downloading Chrome updates or, WhatsApp updates inside your network are downloading the crap ones that you did one-time costs to target all of them or something like that. So it's like all this sort of belts and suspenders for all these various things.
We also should mention that like it's not just the binary now, right? That any lots of modern software is remotely controlled by the vendor, and like every single one of those things is potentially the number of different knobs that a modern piece of software has, each of which have turned the wrong way, can be very, very dangerous, extraordinarily high. As a concrete example, what if you update the root list, right? Is the root list compiled in, or is the root list just a file, right? So I don't know. I don't know like what Chrome has, but like, do you have a knob for testing that like suppresses like certificate validation? So like, basically every single thing that has any impact on the behavior of the system has to be treated the same treatment. So like, I think you're right. I think this is something which has value. I just, the question is like, where are we going to spend that sort of relatively small amount of resources we have on this? And I sort of, when I thought it was easier, I was more enthusiastic about it. And now it seems to be, everyone has done it. Like, as you say, the only people that it seems to be Chrome, and it seems to take them a really long time. And so I sort of wonder, like, how hard is it really? And is the juice worth the squeeze?
Yeah.
It was worth the squeeze in like PKI to bring it back to CT, right? Like we were in a world where like the best way to attack Google users was to like own DigiNotar and then man in the middle of their traffic. And now like that doesn't happen anymore.
I think undoubtedly.
Yeah, we're also like we don't talk a lot about like the CT wins, but there are like not just like the conceptual response to DigiNotar, but like I think CAs have been distrusted because of CT.
Oh yeah, definitely. I'm going to bring us all the way back to the beginning, which is doing things securely on the web. We've talked about network layer security. We've talked about transparency. We've talked about privacy. How about I just want to write a web app or a website and make sure that I can like do it with a secure software model so that, say, I want to do, I don't know, like an end-to-end chat I can do end-to-end encrypted video calling and things like that, sort of, if it's ephemeral. What if I wanted to deploy software with some of the security guarantees that I get if I deploy an app in an app store for your iPhone or your Android phone, I think there's been some stabs at trying to not quite do things that are binary transparency for the web, but just sort of like web app security improvements. Do you see anything in that arena? Do you think it's actually going to like improve web devs' lives anytime soon? Because I just keep seeing like WhatsApp deploying, like make sure you install our Chrome extension so that we will actually like check that you're running the correct version of our website that's connected to your WhatsApp account, so that you can run WhatsApp web securely and
like
things
the
like that.
I mean, like,
yeah.
And that's dependent on Google or Meta and Cloudflare's relationship. And it effectively has the property that all it does is verify that Meta and Cloudflare have not, one of them is not serving two different copies of the app to two different people, which is a pretty weak guarantee.
I think you can obviously you could, once you have the add-on, you could make something that was better than that. Though I see why, I think, it's probably more like to dial back the threat model for a second and talk about threat model, right? There are two threat models you have to be concerned with, right? One is, the traditional web threat model, of course, is like this, like anything it wants. And only is concerned with like other people who are unauthorized, messing with the site, hence like CSRF and XSS and stuff like that. And so then there's I think in the zone, you're talking about a weak threat model, a strong threat model. The weak threat model is, I don't want any clown who controls like access to like the Facebook site or the WhatsApp site to be able to deploy things that compromise the user. But like you're trusting like Facebook at large, right? And so like an example of that would be the Facebook, could say, want to build something that made it so that random engineers couldn't compromise your chats. But so you can imagine a code signing kind of thing, but without a transparency mechanism. And the idea would just be to gate access to the site. So like ordinarily you have some site where it's like anybody can push to who works for the company. And then you say, well, actually only 3 people are allowed to like sign no binary builds, right?
Yeah.
And I think, and you see this, in internal software companies where, you have like a team of developers and like hundreds of people can commit to the thing, but only 5 of them can do a release, right? And so that's like the weak model. And the strong model is, I'd like to be assured that no matter how malicious the site becomes, they can't access the data. I think that's like a much like, and I think there's also kind of like a kind of forward secrecy version of this, which is to say that as you indicated earlier, right, the properties that end-to-end encrypted video calling are supposed to provide is that as long as the site isn't compromised at the time you're doing the call, that no one can read the data, right? And that just doesn't work for messaging because of the persistence properties of messaging. But the site that, WebRTC does not provide is if the place been compromised at the time you're making the call, then it's like game over, right? We spent some time actually trying to address this problem with WebRTC with, I think, very like limited success. Like we designed a whole mechanism where like the audio and video would be like isolated from the site, and there'd be digital signatures and blah, 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 and like end-to-end authentication, and like kind of tried to build through the affordances of WebRTC, and like no one wanted it. So that tells you like, now you can say like we misdesigned it, which is entirely possible, but we took a stab, and it wasn't like, talk about momentum, right? It wasn't one of these things where people would sort of call us and say, well, this kind of stinks. Could you make it better? It was like people were like, well, cool story, but we don't want it. I hear there's interest in this in the MLS world in terms of what's sometimes called web MLS, which is the idea of embedding the MLS stack into the browser. There's noise about this. Like, I don't know how much signal there is, but there's noise about it. I think what you're going to see, I've seen discussions of designs. Emily Stark had a nice post looking at this. I think that was like really kind of like leaning into the BT version of this, namely like that had to validate, if I remember correctly, like the idea was to validate the binaries. There's another version of this that is like a sandboxing version where you say, well, no, actually this stuff has to live in some isolated sandbox, and that's the part that's protected, and everything else is like is access. The complicated problem, I think, is that look, websites are very dynamic objects, right? And if what you're going to say is actually, and what I mean by that is like there's all this different binaries that get loaded, and there's like, people change them constantly, much more than software releases. And so what kind of statement are you actually making? Yeah, and David, you said a minute ago, you serve one version of one person, another person. That's like the normal state of affairs on Facebook, right? Is like they're running A/B tests, and it's like one person gets one person gets the other, right? And so the statement you would allegedly make about binary transparency on an application is there's a very small number of copies of the application, and you got one of them. And the statement you would make about about binary transparency in a website is we serve 500 different copies of the website in the past 20 minutes and you got one of them. Like, I just don't understand how that really works. And so I think we have to step back and ask what the sort of the security property you're trying to enforce is before we even talk about mechanism. And this is one reason I think why people are trying to cabin the pieces of the system that can access the dangerous parts, right? And so, like, if you said, for instance, that, and we're just spitballing here, obviously, but like all the crypto was in some box that you actually can't access from the from the JavaScript, and all you can access the content, then maybe it's a slightly better situation. Probably not that much better, maybe a little better. So I don't know. I'm like actually pretty worried about the whole thing. And I think, our story right now is if you really want that, you have to run an app.
Yeah. And on like the, you're serving 5 million like recently changed versions of the app because of like some of these are, we just have a bunch of options and we want a bunch of options reasons from a application server. Part of it is also like the dynamics of the application platform as well, which is like you just inline things into your web page, however you want to do it, either into your JavaScript bundle, into your HTML that you're actually rendering on the fly. And that's how you configure the thing for a specific user that you've identified via cookies or any other identifiable information, maybe something in the URL. And then on the other side, in like a platform like a mobile app, it's costlier to configure something for every individual user. So you do like one per language or one per or region or something like that. And then you shove in the configuration via like a configuration blob that you either download or cache or, whatever. I could definitely see, I've worked on web apps that are more like the latter than the former, but the former is also completely viable in the world. And like, depending on your scale, you might favor that because you can just do it all dynamically with compute on the edge and you just offload things. Like there's a bunch of stuff that can like favor one of the other, but I wouldn't be surprised if like there were developers that lean towards that application model because it lets them to do this development a little more securely on the web.
I do want to say, I don't think the end-to-end encryption, even if it's entirely in JavaScript, is entirely worthless. I don't think it's great. But if you look at the way, if you look at, you say, what is your concern? And your concern is, very different if all this data is in the clear and logs on the server than if you have to actually serve malicious JavaScript to somebody to exfiltrate it. That's like a very different kind of concern. And so I do think that like, the more that we did end-to-end encryption, even on the client, even if you are ultimately trusting the site to provide you with valid JavaScript, that's like an incremental improvement. And then maybe something later we can figure out how to make sure the site provided you with valid JavaScript. But it's still be an incremental improvement. And like, if I think the theme of this entire conversation has been incremental improvement is the way the web advances, the way the internet advances, right?
Yeah.
I think there's like room to write a systemization of knowledge paper or similar that just attempts to tease out like the full spectrum of security property and threat model for the vague space of like integrity and binary transparency for applications and web applications specifically, because I think these things end up being really difficult to talk about. And like there's obvious things that are like obviously good, like if that one video call provider was able to do MLS on the web, like that would clearly be good to have the video be encrypted on that call for the life of it. But that's, a different threat model from Signal, a different threat model from Facebook Messenger, and being able to articulate that better, I think would be highly valuable.
Yep. Not it. I'm not writing that white paper. But it's interesting because Facebook Messenger just rolled out end-to-end encryption for all of its clients, including its web clients, and they forced it into the existing expectations of their user base. They had a deployed user base and a deployed feature set, and they didn't want to just like take all of their users and just be like, cool, now you're end-to-end encrypted, and also none of these features work anymore because you're end-to-end encrypted now, and we can't do all of this fancy shenanigans we used to do on the server for you because we don't have access to your messages. They didn't do that. They re-engineered a whole ton of stuff to keep the feature set complete, but it also forced them into solving a whole other backup and storage of plain text information and securely backing up plain text of messages that they call Labyrinth. They did a whole bunch of other engineering that they had to do securely to route around this sort of stuff. And it's just, it's figuring out whether actually that could be a whole other conversation about where's the margin between making these incremental improvements and getting this like bang for your buck, better than nothing improvements versus it is worth it to do a very large investment in a significant overhaul with the caveat that not the web and the internet is not the same as Meta, who controls all of their endpoints and controls not the web, but they control Facebook.com and Messenger.com and all this sort of stuff. They control a lot of the stuff to make that sort of huge overhaul happen that's not necessarily doable on the internet at large. Anyway.
Yeah, it is my feeling that we could probably go on for 6 more hours. So I guess like, you know, if I was going to wrap this up one way, I would ask Eric, like, so you've been doing this forever. We've come like a ways from standardization and thinking about threat models from like, you know, the bad old days in the late 90s where the IETF chased Phil Rogoway off the list because he was pointing out the CVC thing, to where we are now where we have a panel of people doing formal verification stuff. I'm guessing you would tell me that you're pretty bullish about how things are looking for standardized interoperable cryptography done by groups of smart people and like a linkage between academic cryptography and practitioners and the people that are doing the standard stuff, right? Like, I'm getting like an optimistic vibe from this, even though we're talking about like failure modes and everything, right? Like, am I crazy?
No, I think I'm very optimistic about it. I think that I was kind of worried, frankly, after 1.3 that we kind of, all those people were going to run away. You know, a side effect of like doing MLS is we kind of managed to keep them involved. And in fact, I think, you know, managed to actually have, in some ways, a dynamic where they were even more involved, where they were doing a lot of the main design work. So I think that was really fantastic. And I think that things like this, this review panel, I think are another way to keep them involved. I think that, you know, the thing we took us forever to figure out was how to make it a win-win, how to make it so they weren't just doing community service and how they were getting something out of it. I think that's started to happen now. People recognize this is real value. I think, as I sort of indicated, I think the next frontier is showing that not only can the people who are, you know, effectively protocol academics, you know, make progress in doing work, but that new primitives have a place in standardized protocol deployment, and that we can take those new primitives and bring them out in a finite time. Because, like, you know, when I talk to academics, what they're most concerned about is impact. And so if you build something cool, they want to make sure it goes out there. And so if we can tell them, look, you know, this is great, and with a fairly modest investment from your side, we can actually get that out there, then I think that there's a really good story here. And I think we have several success stories, VOPRFs, and, you know, hopefully now PRIO and things like that as well. And so I think if we can keep that rolling, I think we're actually going to be in pretty good shape. I think it's like, I'm pretty happy that it's turned out. I felt like the communities were not talking well, and they're talking a lot better now.
Yay.
Awesome. Well, that is a good place to leave it. Eric, I've been a fan of yours since I was hacking on SSL dump. It's been very awesome hearing all this stuff and getting to talk to you. So thank you so much for taking the time to talk to us.
Thank you for having me.
And Security, Cryptography, Whatever is a side project from Deirdre Connolly, Thomas Tatchek, and David Adrian. Our editor is Nettie Smith. You can find the podcast online at SCWPod and the host online at Durham Chrysostom, at TQPF, and at David C. Adrian. You can buy merchandise at merch.securitycryptography.whatever.com. And if you like the pod, give us a 5-star review on Apple Podcasts or wherever you get your podcasts. Thank you for listening.